Welcome to lecture number 46, and we have been discussing Scott connection, which is used to transform a 3-phase voltage to a balanced 2-phase voltage, and for this you require two transformers. One transformer is B1 B2 and its corresponding secondary terminals is also B1 B2, and another transformer which is a separate transformer of terminal markings capital A1 A2 and small a1 A2. What is the thing we discussed? The number of turns of the secondaries are same, and the primary number of turns of B transformer, that is B1 B2 turns in B1 B2, if it is N1, then number of turns of A1 A2 should be root 3 by 2 into N1. So that the voltage per turn in both the transformers becomes same. Okay. And we drew the phasor diagram. It is better we draw that. So, that once again, and the phasor diagram will be the supply is balanced 3 phase with phase sequence AS, BS, CS. So, this was my primary voltage AS, BS and CS. AS happens to be also A1 and BS happens to be B1 and CS happens to be your B2. Now, the question is what will be the applied voltage across A1 A2. Mind you, in this transformer B, primary has a tapping at 50%, okay, and that point I called O from this point, such that the number of turns this side, that is N B1 O is equal to N B2 O, these are equal to N1 by 2. Total number of turns is N1 and the number of turns of this transformer is root 3 by 2 into N1. And so, this is the thing, and now the question is what is the voltage applied across B1 B2? It is BSCS, that is this voltage. Since B1 B1 are dot, so you will get on the secondary a voltage here which I should call B1 B2, that is straight enough, straightforward. Okay. Primary side, the question is what is the voltage applied across the primary of transformer A. This point, mind you, is O, because it is between BS and CS at midpoint. So, this will be O, and this point O happens to be your A2, O and A2 are same. Therefore, voltage applied across the primary of transformer A is this one, which is at 90 degree to voltage applied to the transformer primary B. Therefore, you will get a voltage here which will be parallel to A1 A2, and if you join this A2 and B2, then the phasor diagram tells you that this will be A1, this will be A2. Suppose the line to line voltage applied is VLL. Therefore, voltage applied across the primary of B transformer is VLL, number of turns is N1. So, VLL by N1 into N2 will give you the voltage here. If I write voltage V B1 B2 will be VLL by N 1 into N 2. What will be the magnitude of the voltage applied across A 1 A 2? Available voltage across A 1 A 2, it will be volt per turn of this transformer, which will be VLL by root 3 by 2 into N 1, is not? Now, this voltage applied across the primary is not VLL, but VLL sin 60 degree. So, this is into root 3 by 2, that is the primary voltage applied across this one is A 1 O, which is VLL sin 60 degree, that is VLL into root 3 by 2 and its number of turns. And so, that voltage per turns is once again VLL by N 1 and this into N 2. So, magnitude of the secondary voltages will be same, and that is why you require the number of turns of transformer A to be root 3 by 2 into N 1. If you take same N 1 turns, voltage per turn will not be same. Our goal is to get a balanced two phase voltage at the secondary points. So, this is the star point and that is what we did, and then we will connect a load here, say a balanced two phase load. Balanced load, suppose Z bar and write Z 2 to indicate secondary load. So, this is a balanced two phase load and these are the voltages. Then what I told you, this point is crucial, that when you connect a balanced two phase load, on the secondary side there will be balanced two phase current. Let this current be called I A, where this I A will be depending upon the power factor of the load. This I A will be here, lagging this voltage by the power factor angle theta 2, that is the thing. Similarly, in the B phase, B 1 B 2 same load I have connected. So, this current, these are the line currents, I B will be also lagging this by same angle, I B phasor, and this angle too will be theta 2. Obviously, since these two phasors are shifted by same angle theta 2 and angle between the voltages were 90 degree. So, this angle too will be 90 degree. So, a balanced two phase current will be flowing to the load. Now, the question is, okay, you have been able to transform a balanced three phase voltage to a balanced two phase voltage. Now, if I want to examine what will happen to the currents on the three phase side, will it also remain balanced or not? The answer we will soon see that it is yes, and how it is to be calculated. Therefore, I know I A, what will be my I A S, that I want to find out, what is my I B S and what is my I C S. From where shall I find out? Secondary currents are known, I will calculate reflected currents on this side, and if we see that I A S, I B S, I C S are of same magnitude, but 120 degree apart, then I will conclude that the AC side current is also balanced. Now, how do I do that? To do this, you have to balance the MMF, follow the rules of sort of ideal transformer, like the MMF of the secondary through the dot current is coming out. So, that is N 2 into I 2, this must be equal to through the dot current is drawn in, it must be equal to I A S into its number of turns root 3 by 2 into n 1. Therefore, you know I A S will be equal to 2 n 2 sorry 2 n 2 by root 3, and here I made a mistake, it is not I 2, but I A, small I A into I A by n 1. This is equal to I A S. This is the thing. So, therefore, I A S, how to draw? This is I A. Your I A S will be in same phase with I A, because this is only a scaling factor. So, your I A S will be, suppose, in same phase with this, with I A S. See, we are using whatever we have learned from single phase transformers, be it the transformer is operating as single phase, 3 phase, 2 phase, individually secondary and primary coil, the relationships they must be maintained, that is there will be a reflected current and so on. So, this will be your I A S. So, I A S is known. Now, the question is how to calculate I B S and I C S. This part you have to go carefully. So, these are the dot terminals. So, through the dot current I B I have shown coming out. Therefore, the MMF of the I will use different color for these calculations. So, it will be this one N 2 into I B. Feathers, I B is feather, I am not drawing bar over these things. This must be equal to the MMF produced by the primary coil, and I should always take currents going into it through the dot, the same logic. But here the problem is current in this portion 50% turns, and in these portions they are different, but no problem. So, what I will do for this n 1 by 2 turns, that is B 1 O turns, it should be I B S into n 1 by 2, I am sorry, n 1 n 1 by 2. And for this part current flowing in this direction, that is I C S, or I can say minus I C S is flowing like this from right to left, I can say, and this is dot means this is also dot. So, through the dot what is the current flowing? Minus I C S into n 1 by 2, n 1 by 2, that is the thing, which means that therefore, we get I B S minus I C S, these two terms is equal to 2 n 2 by n 1 into I B. So, this is another important equation, because I A S already I know and I have drawn it in terms of I A. I want to know in the similar way what will be I B S and I C S in terms of I A or I B, whatever it is, secondary currents, because I A and I B are known, these blue colored feathers, from that we are trying to get. So, I require then another equation. What is the another equation? Another equation is, in this side if you look at it, we know IAS plus IBS plus ICS, these are all phasor sum is equal to 0. That is the third equation. Therefore, I get that IBS plus ICS is equal to minus of IAS, is not? That is what I get. So, this is the third equation. These two equation is to be solved to get IBS and ICS. So, add them and divide by 2, you will get IBS supply current on the 3 phase side in the B phase, IBS will be equal to adding these two, that is minus IAS and minus IAS and plus of 2 N 2 by N 1 I B by 2 IBS you will get if you add them, and similarly if you subtract this and this, you will get ICS 2 ICS is equal to minus IAS by 2, this minus minus 2 N 2 by N 1 into I B by 2. So, this 2 goes. So, finally, what I get? I get I will repeat that all the 3 currents. What is this color? We got IAS, IBS and ICS as IAS is 2 N 2 by root 3 N 1, that is this one. Why not I am copying and putting it. So, I will get IAS here, okay. And so, this is the IAS, and what is IBS we have got? I am just I will take straight away from this. It is okay, let me write IBS is equal to minus IS by 2 and this one. So, I take this, copy it and paste it. That is all. So, this is the thing I have got. I will put it in the corner so that I can do something. So, this is the thing IAS, IBS and ICS, and let me draw the phasor diagram of the secondary side voltage and primary. So, that phasor diagram is also needed to indicate that. So, it was like this A 1 B 1 and this is A 2 B 2 and primary phasor diagram was like that AS, BS and CS, and this was the point 2. It was like this. Now, these currents where you recall I A and this current was I B, their lengths are same because balanced load I have assumed, and this is the power factor angle theta 2. Now, from this you can see that IAS will be in phase with IA, and if I just want to sketch here taking some arbitrary point, it need not be neutral, just superimposing this current, then IA should be like this with vertical theta 2, it will be IAS in phase with IA, and here I draw that. Okay. This is the thing. Then if you see IBS, it is equal to IB is like this. So, N 2 by N 1 into IB. So, this part, suppose IBS I am plotting, it is this term. So, erase this 2, it is not there now. So, N 2 by N 1 into IB, IB is here multiplied by N 2 by N 1. So, it will be here this is equal to this part N 2 by N 1 into IB. To this I have to add minus IAS by 2, this is IAS. So, to this you add minus IAS by 2, and then you will get IBS. Similarly, ICS is N 2 by N 1 into IB, negative of that. So, N 2 by N 1 into IB has already been drawn. So, negative of that, this length is minus N 2 by N 1 into IB, and to this I have to add minus IS by 2. So, IS minus IS by 2, this is minus IAS by 2, and then this current will be your IC. Is that clear? So, the reflected current, and mind you what is IAS? IAS is 2 by root 3 into N 2 by N 1 into IA, and mind you magnitude of small IA and magnitude of small IB, they are same, you know. So, this is the thing, and obviously, this angle is 90 degrees because I have shifted IAS by theta 2, same angle. Similarly, IB is shifted by theta 2. So, this angle is 90 degree. Therefore, I must show, if I can show that this angle is 30 degree, then I will conclude that it will be a balanced 3 phase currents. That is the thing. That is very easy to prove. You calculate tan alpha from this right angle triangle, tan alpha is equal to length of this. What is the length of this? IAS by 2. So, it will be 2 by root 3 into N 2 by N 1 into IA by 2, half. This length I have to, no negative sign, just from the right angle triangles, this divided by this one, and that is equal to N 2 by N 1 into I b, the magnitudes. I b magnitudes are same. So, this will cancel out and this cancels out, this cancels out, and you are left with 1 by root 3, which indicates that alpha equal to 30 degree. Similarly, from this triangle, this is also alpha, has same ratios. Therefore, we conclude that when the secondary current is balanced two phase current like this, when Z 2 are same both in magnitude and power factor angle, then secondary current will be balanced, but it will also ensure that the current drawn from the three phase side will be also balanced. So, it is a very nice connection. You require two single phase transformers which are not identical in the sense that number of turns are different. Primary side must have a total number of turns N 1 and with a 50% tapping, otherwise you cannot implement that. The second transformer primary must have its number of turns same as this transformer, but with root 3 by 2 into N 1 turns. Secondary turns are same. So, what actually people do is this, they say take two identical transformer having same turns, this is also N 1, this is also N 1, this fellow primary, one primary should have a center tap, another primary should have a tapping at root 3 by 2%, that is 87% or so. You understand that. Anyway, this is I do not want to complicate the figure by drawing that, because this is the thing and you get balanced two phase system. Acha, if I say that okay, it is just a question, if you have understood it correctly, suppose you have a supply neutral also available N s, and I ask you, can this N s be connected to somewhere in this circuit? See, star connected load supplied from a 3 phase 4 wire system, neutral is straight away connected to the star point, is not, and ABC are in the other three. Now, I am asking you, it is not a star connection although looks like star, this is one winding, this is one, this is one. Suppose I ask you where this N s can be connected to, not at O, you should not connect N s here, where it should be at the centroid of this supply triangle and it will come over here, and that I can calculate how much it will be, centroid it is. Therefore, at this point which will be here, and I can specify at what tappings you have to take to connect that, is it? So, this is how a Scott connection will behave. Only one last point is this, that this diagram I have drawn for balanced load, but these equations are true for balanced and unbalanced load as well. What I mean by saying that, with unbalanced load what happens? With unbalanced load connected load on secondary side, no problem, because what I will do is this, the secondary voltages are balanced, A 1, A 2, B 1, and this is A 2, B 2 neutral, and suppose the load you have connected such that it is I A, and in the other phase you have connected a load I B whose magnitudes may be different, and these two angles is not 90 degree. So, it is a unity power factor load, primary power factor, but what I am telling is this equation remains intact. MMF balance equation will not change. Only thing I will be deprived of this simplification, that is magnitude of I A is equal to magnitude of I B. We crossed out separate thing, no. So, it should be then I A, its reflected current will be I A S is this I A you have to take in phase with this. I will just indicate it. Similarly, N 2 by N 1 into I B, this time it will be like this, getting me, and minus I A S by 2 if you join. I will just indicate, it is your duty to study that. So, it can be done unbalanced load, and you will see that primary side current is also not unbalanced. And also note that the primary current will be balanced, and what will be the power factor of that balanced current drawn from the supply? Same as theta 2. Why? Because this is the phase voltage of the primary side, and I A S lags it by an angle of theta 2. If secondary current is unbalanced, primary current is unbalanced, but what I am trying to tell, these equations I A S, I B S and I C S, these equations are true no matter whether balanced load you have connected or unbalanced. But if it is unbalanced load, I will not be able to use this information, and that is why this angle alpha etcetera will be different, and not it will not come so nice as 1 by root 3, why it should. Got the point. So, Scott connection is a very nice connection, and another thing I will ask you to explore is that this connection, that is this side connected, this is this side connected. Suppose I plan to apply a two phase voltage to this side, shall I get a balanced three phase output voltage on this side? This you please explore. Got the point? That is what I am telling is in the reverse way it will work. That is, this is the secondary two coils and primary connection is like this. I will just indicate it. I have planned, okay, 3 phase to 2 phase it does, 3 phase supply give here, balance 2 phase you get. But suppose I supply this with a balanced 2 phase voltage, this side, should I get a balanced 3 phase output voltage here? Draw phasor diagram and you will get the answer. Reverse way, suppose secondary side, because in any transformer after all, whether you can energize primary, secondary side you get something, secondary side you energize, you will get something in the primary. Anyway, Scott connection is popular because of the fact that two phase supply is not readily available. What is available is 3 phase supply, single phase supply, these things are available in your lab or whatever it is. And if you have a 2 phase load, for example, a 2 phase induction motor or things like that, or a 2 phase furnace, then Scott connection you have to use, and of course, balanced loads are preferred. Okay. So, thank you for this lecture. We will see what we can teach in the next lecture.